Swayam Prabha. Digital India. Educated India.
Yes. So good afternoon. Today, so far in previous 2 or 3 classes, we were trying to understand about we were trying to solve some problems based on our pericyclic knowledge. We included many reactions like electrocyclic ring closure, ring openings. Then we tried to understand. We used our cycloaddition reactions and sigmatropic rearrangements like 3,3, 1,5. So using this type of reactions, we tried to solve many of the pericyclic problems. Okay. So what we are going to do in this class is that there's another important class of pericyclic reaction which we have to study, that is your chelotropic reactions. So today class we will try to focus on chelotropic reactions. Okay. So chelotropic reaction. So what is chelotropic reaction? Chelotropic reactions are special class of pericyclic reaction. They are special class of pericyclic reaction which involves both cycloaddition and cycloreversions. Fine. So chelotropic are special class of pericyclic reactions which involves either cycloaddition reaction or a cycloreversion reactions. So cyclo breaking up. Okay, it should be either a cycloaddition type of reactions or it should be a cycloreversion. So if you define them, what is that? If you see the definition, it says that chelotropic reactions are those in which, keep in mind, chelotropic reactions are those in which 2 sigma bonds are formed. You have seen like in pericyclic reactions like formation of 2 sigma bonds. Okay, and you have seen cycloaddition reactions where you can form a new 2 sigma bonds, but how far it is different in chelotropic reactions. Chelotropic reactions are those in which 2 sigma bonds are formed on same atom. Okay, that's more important. This is more important. So 2 sigma bonds are formed on same atom. It can be one, or you can also say that the reactions in which 2 sigma bonds, 2 sigma bonds are broken on same atom. That's very important. So what's chelotropic reaction by definition? Chelotropic reactions are reactions. Okay, it's a important class of pericyclic reaction. That is the first thing. Okay, it's a class of pericyclic reaction. It can be either a cycloaddition or it can be a cycloreversion. So how it is different from other pericyclic reaction is that in chelotropic reaction it forms a 2 sigma bond on same carbon atom, or 2 sigma bonds are broken from the same carbon atom. Then you call these reactions as stereotropic reactions. Once we see the example, you will really understand the definition. Okay. First we will see, because I said there are two classes, right, cycloaddition and cycloribation, that is 2 sigma bond forming on same atom and 2 sigma bond breaking out from the same carbon atom. First we will take 2 sigma bonds formed on 2 sigma bonds formed on same carbon atom. Okay, same atom, not carbon, same atom. So we will see some examples for that. Then you will know that you can understand the definition much more better. So you take a diene, fine. So it is a diene. Then I am taking a system, sulfur dioxide, fine. So you have a system like a diene here and you have a sulfur dioxide. So if you see, this can be a 4 electron system, 2 electron system. So you have a 4 electron, but if you see the atom, the atom involved 1, 2, 3, 4. In this case it is only 1. Okay. With respect to atom, I can write this reaction as 4 plus 1 cycloaddition with respect to the atom. Okay. I can write this reaction 4 plus 1 cycloaddition reaction, nothing but fine. But if you see the electron, it is 4 plus 2. Okay. But with respect to atom, I am talking about 4 plus 1. Now if you draw the product, right now do not worry about the stereochemistry, I will just come back to the stereochemistry later, we will discuss that. Now see the definition, what the definition said now. The definition says to you is that 2 sigma bonds will be formed on same carbon atom. Here you see I am getting, this are the 2 new sigma bonds, right, new sigma bond, and this is your new sigma bond, and they are formed on the same atom. Now, okay, 2 sigma bonds formed on the same atom. Then you call these reactions as chelotropic reactions. Any doubt with the definition? Anything? Okay. Then we will take some other examples. It is not that it should be only on the carbon atom. You see, we are taken on the sulfur. So we can see several other examples where you can use your carbon atoms like that. Okay. So we will see the next example. I can take the same diene system, I am saying the same system. Okay. Instead of sulfur dioxide, in this case I am going to take carbon monoxide. Clear? Now again, if you see what system it is, how many atoms? 1, 2, 3, 4, 4 plus 1. So I can call this as 4 plus 1 type of cycloaddition. See, don't worry, I am not talking with respect to electron, I am talking with respect to the atom. 4 plus 1 cycloaddition reactions. So you can think about this product. All right, fine. Now we can, there are one more example which you can try. You can take your Okay, this is not a diene system, this is just an alkene. Okay, your butene type alkene. Then I am going to treat, which is well known reaction, you know, once I write this, yes, it's a carbene. Okay, I have studied this reaction in many cases. Okay, now if I see this again, it is I am going to do 1 2 and here 1. So, it is 2 plus 1 cycloaddition in this case. And I can get you. So, just a carbene addition which you have studied in detail. Okay. So, you get this product. Clear? So, this type of reactions, okay, where you can get two new sigma bonds, okay, on new sigma bonds, two new sigma bonds on a atom, on a same atom, then you call this reactions as chelotropic reaction, and this is under the head of formation, that is cycloaddition reaction. There are other reactions also. Another type is that which can be of chelotropic nature, that is chelotropic reaction, that is you call cycloreversion type of reactions. In cycloreversion reaction is two sigma bonds, okay, broken from same carbon atom, because your definition has 2 there, right, same atom. Can be either 2 sigma bonds formed on same atom or 2 sigma bonds broken from the same atom. So, examples for this, we will see some examples. So, okay, azo compound, I have taken this compound and this on slightly heating. Okay. Now, what will happen? You can see in this case, so I can write a diene coming out from it and the nitrogen, right. Now, what happened here? You have 2 sigma bonds, these are your 2 sigma bonds, and these 2 sigma bonds are broken from the same carbon atom. So, they fall under the class of chelotropic reactions. Okay. There are many examples which you can draw. This is one of them. You can also try to do with your 3-member ring. See, in this case your nitrogen elimination is there. You can have where even you can think about your carbon monoxide elimination, okay, giving you alkene plus carbon monoxide, fine. Then there is one more, even you can, because you have seen like sulfur dioxide adding to your diene system, right. Same way you can see extrusion of sulfur dioxide, for example, in this case. So, it is a, now we have a system like this, in heating you can see nice extrusion of your sulfur dioxide. You can happily push your bonds here, giving you what you get. Yes, you get a nice triene plus you get an extrusion of your sulfur dioxide. See, so this is what we call as chelotropic reactions. Now, if you read back your definition, what it says, you can understand now better. Chelotropic reactions are reactions in which two sigma bonds are formed on the same carbon atom, or two sigma bonds are broken from the same carbon atom. So, we have seen the examples for that, like addition of your carbon monoxide, addition of your sulfur dioxide, carbene addition to your alkene systems. Same way you have seen extrusion of nitrogen from the azo compound, carbon monoxide, sulfur dioxide. This all falls under chelotropic reactions. Any doubt? Okay. Once we are now fine with our definition, then we will slightly see the stereochemistry, which you have understood. You have already have seen that, but anyhow we will just get back to the stereochemistry one. Just this type of chelotropic reactions are morely highly stereospecific in nature, these reactions. Okay. For example, I'll just take already I have shown this, I have taken a diene system with my sulfur dioxide. See, addition of your alkene with your carbene you have studied, and you know they are stereospecific reactions, particularly singlet carbene, right? Because triplet carbene, you know that it goes by radical mechanism, that is why the stereospecificity is lost. But in singlet carbene, you have studied that it has to your alkene in a concerted fashion to give you a stereospecific product, that we have discussed during the carbene formation in earlier classes. Okay. Same idea, same analogy we can apply here also. So, this reaction I will take for sulfur dioxide, because you know the carbene. So, you get this product, right. But if I take a diene of this nature, then treat it with sulfur dioxide, think about what you get. You get a system you get a very specific product. In both the case, you get a specific product. We can understand this from the orbital interaction better, because if you know the HOMO and LUMO of these systems, so you can understand them better, why you are getting specific products. Just I will show you, because you know them in detail, but just I will refresh little bit. We will see the orbital interaction, so that you can regain your things. Orbital interaction you will see. So, I can taking a diene, okay. In one case I am going to take the HOMO of my diene, okay. So, the HOMO should be, you remember, right? Taking the HOMO in one case and see how it reacts with the, then it should be the, if I am taking the HOMO of diene, then it should be the LUMO of your sulfur dioxide. So, we will take the LUMO of sulfur dioxide. So, this is your LUMO of your sulfur dioxide. So, write it this. Right, this should be the LUMO of your sulfur dioxide. Now you see the interaction how it should be, whether it should be intrafacial or it should be suprafacial. See when you consider the HOMO and the LUMO, how it should be. It should be, yeah, it is allowed. It should be nicely suprafacial interaction, so that your stereochemistry is preserved so nice. Okay, just it is direct interaction. So you get the specific products. Same way you can think in other angle also. You can take the LUMO of your diene and the HOMO of your sulfur dioxide and see whether you are, again it is a suprafacial interaction or not. So I will take the diene then. Our diene system, I am taking the diene of this. So I will take the, so you remember the LUMO of that. So I have taken the LUMO, lowest unoccupied molecular orbital, and then I will take the HOMO of your sulfur dioxide. Just we will draw the HOMO of your sulfur dioxide. Then you have then you fix your right. Now if you see the interaction again it is suprafacial. Again it is a suprafacial interaction. That is why like you can see you are getting the specific products, and the reaction is highly suprafacial in nature. Clear? Any doubt with this? Any doubt? Because this is more important about your chelotropic reaction. Just like your carbon, if you just use the analogy of the carbon, yeah, because carbon addition to an alkene is again it is, you can consider them as a chelotropic reaction. Just I use that analogy. I use the HOMO and LUMO in both the cases, and I have shown that it undergoes a nice suprafacial addition. This is for your this is about the stereochemistry of your cyclo addition reactions. Now same way we can see about your cyclo opening also. They also are like little bit specific in nature, like we can see for cyclo opening, because you have seen the ring closures reaction. You can apply your Woodward-Hoffmann rule also, and you can see cyclo opening more like that. So for example, I will take a system like this, sulfur dioxide, which we have studied. Okay, we have a methyl here. Now I am see previous case I have just taken the diene and I have shown that sulfur dioxide goes off. Now I am slowly introducing the concept of stereochemistry into it. So I have this hydrogen. Okay. Now this system, this on heating undergoes only this rotatory. You know what is this? Okay, we have studied in detail. So it undergoes only this rotatory. That is one clockwise, another is anti-clockwise. So it happens this way, giving you. So your methyl in both the cases are out front. So in this case the methyl goes off, out, methyl plus hydrogen, then hydrogen. So see, you get only this product. Okay, what is this? This is hydrogen Z and Z. So opposite directions, yes, E. So if I take the other product like another like same compound, just if I change the stereochemistry a little bit, It is the opposite, like let it be CH3 hydrogen. I just changed the stereochemistry here. Okay. Now if you heat this guy, this one again undergoes a dis specifically. Okay. Now in this case you get a different stereochemistry, different product. That is, you get a CH3H in this case, but in this case hydrogen is out, so your methyl is in with your hydrogen out. See, both the products are different and they are specifically formed this. Clear? Any doubt with this? Okay. See, this is for your like foreign system. Same way, if I take foreign +2 type of system, for example, cannot go for a diene. Okay, that's more like an alkene. If I take it for a diene type of system, we will fix the hydrogen methyl here. Okay, we'll take this product. Now if you heat this, previous case it was dis, right? It undergoes a nice dis rotative. Now it does a con. Fine. So you know how it opens con. One should be, both should be clockwise or both should be anti-clockwise. So both should be clockwise. So one, you get this product. Clear? If I take the different stereochemistry of this product, sulfur dioxide, we will have a methyl here. Okay. How specific these reactions are, that's a key here. Heat, again it undergoes a con. Okay, one should be, both should be clockwise or both should be anti-clockwise. So you can think of, you will have a both outside methyl. So you get this product. Clear? So this is about the stereochemistry of your chelotropic reactions. So we have seen both cyclo addition as well as the cyclo revision. It is you call as extrusion of your sulfur dioxide or carbon monoxide or nitrogen type of compounds. Any doubt with the chelotropic reaction so far? Okay. Now what we will do, since we have seen their definition, we have understood some examples of them, we have slightly went through their stereochemistry, we know them. Now what we will do, we will see some good examples in which chelotropic reactions are involved. Okay. The first thing is that which you have heard about, Ramberg Backlund alkene synthesis, right? You have studied this. Anyone remembers this synthesis? Anyone remembers? No, right? Okay, fine. We will just see that. Okay, we will take a system like this. Sulfur, you have a Cl. This, now both are aromatics. Okay. So now I have a system. Now what I do is this, I lightly put it in base. Okay. What happens in base, your chlorine goes off to get me this product. Chlorine goes off here, giving me a product like this, so that I have this product. Okay, now I get this. This is now really substrate ready for doing your, if I eat this, what it will happen? It is ready to do your chelotropic reaction. Yes, it sulfur dioxide, you can see extrusion of sulfur dioxide from this to give me the final product. To give me the final product without my sulfur dioxide. So, you can see extrusion of this sulfur dioxide, and this is your chelotropic reaction, where your two sigma bonds are broken from the same carbon atom. Okay, this is called, this is in Ramberg-Backlund alkene synthesis. Okay. We see the next example. So, we will take a cyclopentanone type of system, where you have your all like phenyls, like aromatized one. Okay. Now we have this, we will try to ETOC will take this. Now tell me, if I add this and eat, what reaction I can expect. This is CO2 ET, okay, your carboxylate ester of your carboxylic acid. Okay. Now tell me, what type of reaction I can expect from this. Yes, simple. It's a straightforward 4 plus 2 cycloaddition, right, to give me what product? Just write the product. So, I get this cycloaddition product. Cycloaddition reaction. So, you get this product. Now, tell me what reaction you can think of if I heat this. Yes, chelotropic reaction with your carbon monoxide going off. Very good. So, carbon monoxide goes off, you get a chelotropic reaction. Fine. So, your product should be then get an aromatic bag with your phenyl, have your phenyls, then you have your CO2 ET, get a CO2 ET. See, So this is one more example on chelotropic. Like first what I did a cycloaddition reaction, which you know, to give me my product, and this product then on heating undergoes a carbon monoxide extrusion to give me a highly substituted benzene. Fine. So you can use this type of chelotropic reactions in making even you can make natural products ring system like A, B, C, D reactions, or a ring you can build up using these chelotropic reactions. I will show some examples in which they have used it. We will take another example, similar type of examples. So I can have a phenyl. So this system I have. Okay, this is my substrate. Now I say that I'm lightly heat this substrate. Okay, so you know what it will happen. Yes, you have a sulfur dioxide eliminating, and you know it is nothing but it's a nice chelotropic reaction in which sulfur dioxide gets eliminated to give me what product? Just see the product what I get. That will be really interesting. See, it's more like a system with a diene type of system, right? Which is a very good substrate. For what? Because you have a diene here. Yes, you can do very good Diels-Alder reactions on this. So see, that's how you can use your chelotropic. So you have sulfur dioxide. Now you generate a diene from there, and you know that you can either do ring closure with them, you can do n number of reactions using this. Clear? So now if you, for example, I'm showing you, if I treat it with a quinone type of system, like very good adductive Diels-Alder reaction, then naphtha-quinone type of systems, right? Now what will happen? You know, it is nothing but you can do a nice Diels-Alder reaction. See, you get a very nice product. See, that's how you can use your chelotropic reactions. Phenyl. See how I am like building my rings. See, I have made a very nice molecule using my chelotropic reaction. Just I have taken my phenyl type of system, okay, and then just carried out a simple heating, gives me a sulfur dioxide extrusion to form me a diene system. See, this is very important. You nicely get a diene system, which is a good adduct for many reactions. It's a very good starting material. Then you just treat it with your naphtha-quinone type of system, and it undergoes a very nice Diels-Alder reaction to give you the product. Okay. Any doubt with this? No. See, so there are good examples which you can try off with your chelotropic. You can understand them, and you can even enjoy how they are useful and how people are using it for making ring systems. I will show some examples how people are used it for making even ring like A, B, C, D. Take this simple example. I have a sulfur dioxide, okay. Take this system now. This is sulfur dioxide. Okay. Now I say just heat this. What will happen? Normally they take this, they in a sealed tube, you heat it for 300 degrees Celsius, you get your sulfur dioxide extrusion, which is your chelotropic reaction. With your sulfur dioxide eliminating out. So you get very nice product. See, now again what happens once it eliminates, again you are getting a, see, right, you are again getting a very nice dyeing system. See, plus you can write your other molecule. See, you get this. Now tell me what this can do. What this can do now? Yes, that's all. It's again, you can think about your Dill cellar, or it's a sort of ring closure, intramolecular type of thing. That's all. That, see, that's what I am saying. It's so this type of reactions are really good. Okay, it can get here, and you can get. Now, based on this, what you are seeing, you see your product. You will be really interested to see the product. See, now I have constructed two rings. In this case, if you see this, I have constructed a two ring A, B, C. That's what this real interesting part of this. You are taking a system, and now once you do a chelotropic reaction, you are bringing back your dyeing. Then in the previous case, we have seen using this dyeing, I have used an naphthoquinone type, and we did a intermolecular Dill cellar reaction. In this case, you can even, if you think, you can do a intramolecular Dill cellar reaction, and you can think about your, you can construct about your ring system, right. So that's how they are, this type of reactions are really useful. Same construction of ring I will show, like even you can construct A, B, C, D type of rings. We will see another example where we can do that. So what we'll do, we'll take a sulfur dioxide, okay. Methyl, think about my cyclopentanone system, my alkene. Okay, I'm taking this molecule now. Now I say I will heat this. So you know pretty well that it undergoes a nice chelotropic reaction. It can undergo a nice chelotropic reaction, okay, with an extrusion of your sulfur dioxide. So you get a dynamic. See, this type of reactions you should my methyl, this methyl one, and then again the same, it comes to, so previous case same example, same thing, but now if you see, you will have A, B, C, D ring. Now this, you know that it undergoes a Dill cellar type of cycloaddition, ring closure with reaction to give you the final product. Methyl, hydrogen, hydrogen, and your aromatic. See how beautiful it is. What I have seen, A, B, C, D. I have constructed like 4 rings in this case. In earlier class, I have shown that I have constructed A, B, C. In this case, A, B, C, D rings. See, like that, you can use your chelotropic reactions for making, because one always you get in your mind, if you have a chelotropic reaction, you can extrusion, not only it is of extrusion of sulfur dioxide or carbon monoxide. After extrusion, can I make a diene type of systems based on which I can build up or I can construct molecules, because this type of dienes, you know that they can be done, they do these other reactions very nice to give you amazing type of products. Okay. Let's see the last example of chelotropic reaction. N, you have a phenyl here. I can have N diethyl and then my nitro. Here is my nitro. O minus plus. So I am taking a molecule like this. Okay. Now tell me, because it's a diketone type of system, it's a proper diketone. Now I say that I take this system, I heat it. Now tell me what you are going to expect from this reaction. Anyone? Yes, you can still, yeah, you can do a carbon monoxide eliminations. Okay, this can happen very nicely. For example, you can just push this up, okay, and you can get to a carbon monoxide elimination. Nothing but a chelotropic reaction. Chelotropic elimination of carbon monoxide. Any doubt? So you can get this. So then if I write the structure properly, I should get a doubles, because the double bond moves here. So you get a ketene type of structure with your nitro here. Fine. Then I have my N diethyl, this one. Once it moves, I have my double bond and phenyl. See? Again, if you carefully watch this type of system, again it is a type of diene, okay, not exactly, okay, type of diene, type of system. This type of systems are highly reactive also. Yeah. So what you are going to expect from this? Because this is not going to stand like that, okay. So what it is, what it can do? Anyone? What you can think about? What reaction it can do subsequently? Because heating, carbon monoxide goes off, undergoes a chelotropic reaction to give you this active product, and what you can expect from here. Because I am not going to give you anything, it's not like I am not externally adding anything, okay. Now just think, yeah, that's all. It's nothing but it undergoes a, if it is something I have an alkene or something, then you can think about intramolecular Diels-Alder reactions or other types of reactions involved in it, right. But I am not adding, so it should be inside. So whether it is a intramolecular, you cannot do that. So then you can think about your electrocyclization, right. think about electrocyclization reaction. If it is electrocyclization, then it is a 4N, right? This is 4N system, and heating, you know, it is a con 1 to give me. So nicely it will cyclize. You can have a cyclization. What type of cyclization you can think about here? You can have a ketene cyclization with your N diphenyl and nitro out. Just try what type of cyclization you are going to expect. It will be interesting if you write this, because I know that because I have built the molecule in such a way, you might think of doing this type of cyclization, which is preferred. First thing that should come in your mind, because if you see this cyclization, this molecule, okay, it's interesting to watch this molecule. That's why I just stopped writing the product, because I want you have now two ways of electrocyclization taking place, right? I can push my bond, cyclize this one, or because since I have drawn this, that goes in your mind very clearly. I can push this, cyclize, or you can push this and you can cyclize here also. Yes or no? Yes, I can do this pretty well nicely. Clear? So it undergoes this electrocyclization to give you the O carbonyl with my double bond N phenyl and NET2. So I can get this system. This system further undergoes. This is not the stable molecule. Further, you can it can undergo nicely. This carbon dioxide elimination goes off to give you the final product. But subsequently, this can undergo. This is not going to stay like that. Okay, it undergoes the several step. Clear? So this is all about your some examples about your chelotropic reactions. So that's a class of reaction which I wanted you to discuss, because it's an important class of pericyclic reactions, because you can see that both cycloaddition as well as cycloreversion taking place. But one thing keep in your mind, it is happening on the same carbon atom. Clear? So and it is also stereospecific. So to remember the stereospecific, you can always remember your alkene to your carbene reaction. Clear? Any doubt on chelotropic reaction? Okay. So that's about chelotropic, and that's about in this class. In this class, what I will try to do, I will slightly get into one reaction which I have to explain you, that is your ditropic rearrangement, which also falls under pericyclic reaction. It's not big, but just I will introduce you to that ditropic rearrangement, and after that we will do some applications of photochemistry. We will see some new photochemistry has lot of application. With ditropic reaction, your pericyclic reaction is over. After that, I will take you as the last part, I will take some new applications or new field that comes out of your photochemistry. Okay. So for this class it is done. So thanks a lot.